Good morning, good afternoon, and good evening for everyone who's tuning in. On behalf of PioPetro and Millet Research Hub, I'd like to welcome you all in our summer internship program. My name is Mayar Tarek, a senior gas and petrochemicals engineering student, and SPE Egypt Young Professionals member, and I'll be your moderator for today. So before we start, please keep the chat box professional and ethical, and don't forget to drop your questions in the Q&A section below. So without further ado, let's welcome Dr. Ahmed Gomaa. Dr. Ahmed Gomaa is a simulation fluid expert with more than 15 years of experience in different engineering, technology, and academic roles. Since 2017, Dr. Ahmed has been working with BP and as a well intervention chemistry specialist before being a research scientist at Baker Hughes for 6 years. Dr. Ahmed holds a PhD in petroleum engineering from Texas A&M University and has published more than 19 granted patents, 13 peer-reviewed journal papers, and 73 conference papers. Thank you so much, Dr. Ahmed, for coming today, and the mic is yours.
Thanks so much, Mayar, for the
Thank
introduction.
you.
Highly appreciated. Okay, so let's start. Okay, can you see my slide?
Please make it full screen.
Yeah, it is full screen, Dr. Ahmed. Can you see it full screen?
No, I have the slide in the left and have one slide in the middle.
Yes.
So reshare again.
How about now?
Screen. So perfect. Please go ahead.
Okay, excellent. Thanks a lot. So thank you. Thanks for everyone attending the session today. Today we will try to cover some quick introduction about frac fluid. Before we start, let's just have some basic understanding about fracture treatment, what we do and how we do it, and what's the role of the frac fluid. So usually you came up at the surface, you already drilled the well, you already completed with some sort of casing, you already perforating it, or maybe open hole. And what you're trying to bring here, you bring one of the big surface company, Schlumberger, Halliburton, or Baker, coming the surface with a lot of pumps, with a lot of tanks, with a lot of chemicals. And the idea is try to frack the downhole. And the way that they do it, they bring all the equipment at the surface, and from the wellhead, they inject two things. They inject something called proband, which is like a very spherical, round material that will keep the fracture open and keep the fracture conductive later on. And we pump it as a suspension in something called gelled fluid or frac fluid. It's just like jelly material. I will show you later on some picture for this one. It is really like a slurry that you're injecting. And the objective of this slurry is going all the way until downhole, break down the formation, extend the frac, and we injecting both the frac fluid and the suspended proband inside the downhole condition. And as we're injecting, the fracture keep extending and the fracture keep growing as a function of time. Then after we finish the injection, what we need, this gel fluid will be broken and flow back during the production phase, during the initial production phase, leaving the proband back inside the frac. Very spherical material, have a really high conductivity, high permeability, and allowing a better production. So that is simply like the fracture treatment that we do at the surface. And after we do the treatment, if I look to the top section flow, if you have that's your well bore, you will end up with something called bi-wing frac for vertical well. When you have really frac around the well bore, and this frac is filled with proband. A spherical material have a huge permeability. What does it do if you have a frac like that? It's first bypass any damage that's been created during drilling and completion phase. Any damage from mud, from semen that around the well bore, this frac definitely will be bypassing it. A second thing, if you have only vertical well, the production trend or from reservoir engineering, we are talking about radial system. However, if you have a fracture, the production turn to move from radial system to a linear system. When the flow actually inside the reservoir, the hydrocarbon move linearly, and as you move linearly, the pressure drop will be much less compared to the radial flow. And that definitely will accelerate the recovery, will accelerate the production. Thus, by changing the way that the hydrocarbon flow inside the reservoir. So if you have a better productivity, definitely will have a better economics and a better production from the well. So that's like simply what we do from fracture treatment point of view and how we do it. So let me rephrase it again as an like an award. If you're talking about hydraulic fracture, you are talking about some sort of a technique. It's called the stimulation technique. Usually we do it to extract more hydrocarbon, especially from the low permeability formation. And what we are doing, we are trying to provide like a more permeable path. We correct the formation, we create a path that the can hydrocarbon move freely inside this path with a higher rate, with a more production, and the less pressure drop, especially in the near wellbore area. That will help us getting any bypass damage. That will accelerate the production. That's accelerate the recovery from the formation, and definitely the economics and the production from the well is happening. Hydraulic fracture treatment is not something new. The first treatment done 1947, so it is really old technology. But recently, it's become like a more a systematic approach, especially for unconventional shale formation. And as the times go, it become much bigger and bigger and bigger. So if I'm looking at this a picture for a frac treatment in 1990, and at that time, we consider it a really big treatment. We have like several pumps, we have several tanks, we have a lot of water using, but that is at that time called big, and it takes days to do only one job. Since 2000, the job actually become much bigger. You can see how much equipment comparison, much more equipment, much bigger treatment, and instead of taking just a few days to complete one well, we're right now talking about weeks to months. Because especially in the horizontal wells, you are not doing one frac, you are doing multiple frac, may up to 40 to 60 frac per well. And that's take huge amount of time. We're talking about weeks and sometimes months. So with time, the fracture at location, you need more equipment, you need more tanks, you need more water as as going on. So just like a quick picture for the unconventional part, and that's actually a really nice picture from Schlumberger. When you have a two horizontal wells, like this is like a vertical section of the well, and then it's moved to horizontal for two wells side by side, and each part of this is a complete one frac. You can see how downhole is happening. So we are creating a more amount of frac, especially for unconventional. You know, unconventional, the permeability is too small. And the only way you can make it economics is by horizontal well multi-stage frac. That is actually you create like some sort of a pseudo permeability for the reservoir. You crack every, I will not say every inch, but you crack every piece of the reservoir, try to produce as much oil from the shale point. So for right now, if we are talking about horizontal well, usually the vertical section, we can go up to 13,000 feet. And as soon as you reach to your vertical point, you switch to the horizontal section, and we are talking about 1 to 2 miles just horizontal part. And actually sometimes more. Sometimes we'll go like 2.5 up to close to 3 miles just for one well. And right now we're using a much higher pressure for unconventional. We are talking about higher treating pressure, reach to the surface maybe 13,000 psi at the surface to be able to break these fracs and this formation. And definitely with that much amount of frac, you are talking about huge amount of water usage, going from 5 million up to 30 million gallon of water just to treat one well. And this fracture, unfortunately, need a really good quality water. So The more quality water, the better water to use. You will use less chemical from frac point of view, and you'll have a less scaling issue. And that's the current change right now, and that's current trend. If you are looking for current technology in frac fluid, is actually how we can use the produced water. And a lot of companies succeeded, including BB. So when we have a good plenty of produced water, we tend to use it to try to reduce the water quality. And bad part of it, whatever you inject there, you do not get it 100%. Usually get 10 to 30% of the whatever water you are injecting there. So feel free if you have any question to put in the chat. I would really like to have some sort of interaction. So if you have anything in your mind, please try to speak up. So let's focus on the main topic is the fracture fluid and what's actually the composition of the fracture fluid that we have. So 90% of the fracture fluid is just water, just pure water that we're using every day. The better quality of the water that we have is easier for us to work with and to be able to use it. And then 9.5 is sand, which is proven. It's just air material, similar to the sand at the beach. So a lot of people claim like, yeah, we are talking about frac fluid is 99.5 just water and sand. Very inert chemical, has no harmful to the environment. The tricky part was always with this 0.5% of the chemical that we are using, but we are typically using similar chemicals that been applied in the other industry. For example, like we use sodium chloride, like that's salt, some sort of clay inhibitor, and yeah, like sodium chloride is a table salt that in every household use. Ethylene glycol, that is a typical material that can be used in cleaning. Borate, which is a crosslinker for a lot of crosslinker gel that been used a lot in cosmetics. Sodium potassium carbonate, which is our pH buffer, used to adjust the pH of the water. That's used in a lot of the cleaning product and detergent product. And guar, which is one of the main polymer that we're using for generating the gel. You can see it easily in the ice cream that everyone eats and like. And the isopropanol as well. You can find it in the cleaning and deterrent product as well. So we are using similar chemistry that's been used in other industry. And the amount of this chemistry in our frac fluid is very small. And these chemicals, we can divide them in two groups. The first group is the main additives that every frac fluid should have it. And the second group is the additives that we are adding them to be sure we are compatible with each formation. So these additives will be changed depending on type of formation that you are dealing with. The main additives will include the first polymer, which is if you have frac fluid, you have some sort of a polymer inside your frac fluid. And can be guar, can be polyacrylamide, can be other type of polymer, but that's the main two part that can be used. The guar derivative, and polyacrylamide. That's a majority of the frac fluid that you are using. And if you are having a cross-linker gel, definitely we need some sort of a cross-linker, a chemical that will allow to cross-link the polymer, creating this huge, very thick viscosity. Buffer, which usually a pH that either increase the pH or decrease the pH, depending on type of the cross-linker that we're having. Majority of the cross-linker usually is a higher pH. We're talking about above pH of 10, usually between 10 to 11. That's the optimum one. But sometimes we are going a little bit low, like around 9, and sometimes we are targeting a little bit high, around maybe up to 12. That will be depending on the case by case. However, the majority of the cross-linker is between 10 to 11 that has the high pH cross-linker. There is also some marketing for a low pH part for hydraulic fracturing, and usually the target pH is around pH 4 if you are having a low pH cross-linked fluid. Final additives, and the most important one is the breaker. One of the main parameter of the frac fluid is to be able to break and flow back. And will not be able to break and flow back except if you're having some sort of a breakers. So a breaker is a must for any frac fluid. So if you are seeing any frac fluid without a breaker, please put a red flag there. You need to include some sort of a breaker to be able to break the polymer. And usually we have two types of breaker. Enzymes breaker, which is use some sort of a biological material that can be able to generate some radicals to break the polymer. However, enzyme has a limitation of temperature of 200 Fahrenheit. Above 200 doesn't work that well. The other one, which is oxidizer breaker, and there is a big family of breaker at that level. And oxidizer is a well common known, used cover a different range up to 300 Fahrenheit formation without any issue. And that's the one the majority to use from breaker point of view as oxidizer breaker, and it's cheaper. So we like to use it a lot. The second part of the second category, it will be the formation compatibility additives. And that will be depending on the case that you're having. It will be it's morely will be reservoir dependent. So if you have reservoir A, reservoir B, reservoir C, we'll have a different type of additives for each one. Majority of them will be, I will say, like scale inhibitor. Usually that's happening when you have a difference in water salinity between the water that we are using for the frac and the water downhole. For example, like sometimes we are using seawater to do some fracking. Seawater has a lot of sulfate. And downhole, the formation water or the produced water have a lot of calcium, magnesium. So when you're mixing calcium, magnesium, and you're mixing and pumping your seawater, which is having sulfate, you will definitely having some scale, some calcium sulfate, magnesium sulfate scale. You don't want that to happen. That's why we are pumping a scale inhibitor, a chemical that will eliminate the forming of this scale. Second part, clay inhibitor, especially if you're having a sandstone formation and you have a clay there, light, kaolinite, bentonite, all this clay can cause a lot of damaging to your formation. So either swelling or fire generation. So you need some sort of a cationic polymer material or some sort of a KCl, NaCl type of material that will inhibit the activity of the clay, eliminating any damage coming from the clay. Surfactant usually being used if you are having a tight formation and you would like to be sure that you'll have a good flow back and all this water that you are injecting will not be damaging the downhole by alternating the waterability or doing something or increase the water saturation. So add some sort of a surfactant to be sure you have a water-wet environment, and also whatever water you are injecting can get as much as you can out of the water coming out. So your downhole saturation is not very high water saturation, which will affect your oil effective permeability. Biocides is another main chemical that we like to have, and that's help us to kill any bacteria, because you don't want to inject any bacteria from surface to downhole. It will cause a lot of issue. The two type of bacteria that we really hate is sulfate reducing bacteria, which will cause souring to the reservoir, will increase the H2S in the reservoir, and that is a very nasty material we don't want to have. So we'd like to be sure we use something to kill it, which is typically the biocides. Another bad bacteria is called acid-producing bacteria, ABB, and this is again like produce a material that will make your water a little bit acidity. So when you are producing, you will have a lot of corrosion for your tubing, downhole tubing, and your surface tubing as well. So we'd like to kill everything at the surface before we're pumping downhole. Okay. Supplier for frac fluid. The majority of the cases we are depending on the surface company to provide us this frac fluid. We can get it from Schlumberger, from Halliburton, from Baker Hughes, Liberty, Weatherford, whatever chemical company that you are having, usually they have their own frac fluid. However, recently there is a trend that, okay, actually all surface company is good and they can formulate their own chemical, their own additives. However, this chemical is also getting from a direct supplier. We can get it from a direct supplier like Nalco, Solvay, AkzoNobel, BASF, that you can actually get their chemical and formulate your own fluid if you're having your own expertise. If the company have its own expertise that can do it, it may be cheaper and more economical to go this route. If it doesn't, in this case, it'd be better to use whatever surface company offer. And in this case, you already been trialed, you already been invested the compatibility and the performance of this frac fluid. So let's go to, okay, after we know what's a frac fluid, what's the composition of the frac fluid, what's each additives would like to have. Okay, what's a frac fluid do? What we actually, how can it judge if you have a good frac fluid or bad frac fluid? Or what's actually we needed from the frac fluid? Let me have it this way. So there's some parameters that we are really would like to be sure the frac fluid have it and be able to perform this way. The first parameter is be able to transmit all the hydraulic horsepower to the formation. So you are coming at the surface with a lot of good bumps, big bump, generate a lot of pressure and a lot of horsepower at the surface. But you need something to transmit all this pressure, all this horsepower to downhole to be able to break the rock downhole. So imagine you are at the surface and maybe 18,000 feet below you, you like to break the rock under all downhole stress and just to break it and create a frac. So the frac fluid need to be able to transmit this water. The good part, a lot of our frac fluid is based on water-based, and the water is incompressible. So water, because of the incompressibility, it can be pretty good fluid to transmit and be able to break the downhole formation. However, as you're injecting from the surface to downhole, there will be some pressure loss will happening. And the pressure loss, usually we call it friction pressure. And just as you are bumping inside the wellbore, there will be friction, and that's a part that you are losing some of your energy. Let me have it this way. So if I'm producing 10,000 at the surface, you would like to see it, what's happening downhole. If you are losing 5,000 psi in friction pressure, so this means that you are having 5,000 psi lower than what you are generating at the surface just because of the friction. So we need to have the frac fluid to give us as low friction pressure as possible. So we don't have minimize these losses as simply. Second, the viscosity of the frac fluid. We need to have a good frac fluid viscosity because the width of the frac that we are creating is proportional to the viscosity of the fluid that we are injecting. So the higher the viscosity, usually give us a wider frac. And the frac conductivity that's a judgment. We would like to have as higher conductivity as possible. By definition, the conductivity is equal to the permeability of the proppant that you are inject multiplied by the width. So the bigger the frac width, the bigger the fracture conductivity. So that's why having a good viscosity to get a good frac width is really important, because that's actually one of the main parameters that you evaluate your frac. What's the conductivity that you can have it? And you can see from this picture how much viscosity you are talking. That's a cross-linked frac fluid, really high viscous material. Second, suspend and transport proppant. I'm not sure if you can see it here. That's the same fluid at the top, but we have here mixed it with a proppant, which is the tiny browny material there. It's like sand beach. You can see that's a static condition. All this sand is still suspended in fluid. So if you have it, you can do it in your home. If you bring some sand, put it in a cup of water, all the sand will be settled down because of the density difference. You know, water density is 1, sand density usually typically is 2.65. So sand is tend to be settled down and not carried by just regular water. However, if we're having a really high viscosity that we're having here, the sand will not be settled down, will be all the time suspended in solution, as you can see it here. So when you're injecting this fluid, the sand will go with the fluid and will not be settled and will fill the whole created frac that you generated, keeping a good width. When you break it and the frac closes, the sand will stay downhole, covering the whole area. Fourth parameter, you need to be compatible with the formation rock and the fluid. So we need to be sure that we are having no damaging to downhole formation and rock. So that's why we have the clay inhibitor. That's why we have the biocides. That we have the scale inhibitor. We need to be sure that we are not damaging anything downhole from the rock or from the formation that we're having with the oil that we're having or the gas that we're having. And that definitely will help us to minimize any bad impact in the rock permeability or the proban permeability. And finally is the economics. Need to be cheap enough, because at the end of the day, we are doing this one to generate money out of the well. So the cost of the frac fluid should be cheap enough to be able to produce it without any issue. So any question here? I think I can see one question coming. The question is how to ensure transmit horsepower to the formation, not to the casing. So that's an excellent question. So you have the casing. Casing is just the pathway from the surface and the bottom hole. Casing, you cannot, it's to break the casing is too huge amount. So you have a guided perforation, and the perforation will allow all the fluid to go. But casing itself, because of the strength of the steel, is too difficult to break. So usually having, how can I say it, fracking the formation is much at a lower pressure compared to fracking the casing. I hopefully I understand your question right. If I cannot, please rephrase it one more time. What testing procedures are employed to ensure frac compatibility with the specific conditions? So testing, it depends. If we're talking about reservoir condition, so you will have a testing related to clay, which usually the capillary suction test and roller over test and the probant embedment. That is if you are evaluating the clay inhibitor. Based on these three tests, you can see if you are having a minimum damage or not to your frac fluid. If you are worried about the scale, you need to do scale loop testing for the scale. If you are worried about surfactant or water recovery, you need to do Ahmed cell and column test for surfactant point of view. So it depends on the cases that you're having in your condition, and you select the testing that you're having for it. So it's just not only one test, it's just a group of testing depending on the reservoir part that you have. Clay inhibitor will be CST or oven proben embedment. Surfactant column test Ahmed cell. Scale inhibitor will be scale loop test. Biocides will be bacteria killing study. I think that is the majority of it related to the reservoir side. Any more question? So going next, what type of fracture fluid we are having? So usually fracture fluid, we can divide them into main four types. There is plenty of other types like foam, VS fluid, but I will talk about the 90% of today's marketing. The first one is called linear gel, which just usually guar or guar derivative soluble in water. It will give you a 30 to 40 centipoise viscosity. This is a picture of linear gel, and it's very good test and been used usually before the proband pumping, just to be able to create some sort of a initial bad section for the bad section. Then the majority one, which is cross-linked gel. And for cross-linked gel, we have two types of cross-linker, either borate cross-linker and usually that's happening at high pH for guar. Or we have a metal crosslinker, and the metal crosslinker can be titanium. The majority one is zirconium, but can be titanium, aluminum, or chrome as well. And this is you can be used at high pH and also at low pH. And by having a crosslink, you can actually increase the viscosity from linear gel. You can see it from this picture toward this thick cross-linked gel material. You can see just adding a cross-linker, very few GPT. You are talking about maybe 0.1 to 0.3 volume percent, and you can significantly enhance the viscosity from 30, 40 centipoise actually to 500, maybe up to 1,000 centipoise, just by adding a small amount of cross-linker. Then the last two part, which is a more for unconventional, for shale fracking, and right now that is the practice. We're not anymore using linear or cross-linked gel. We're mainly focusing on slick water, and the new terminology for slick water is called high viscosity fracture reducer, HVFR. That's right now, I will say almost 99% of the current unconventional frac treatment using the high viscosity FR. So, and that's the two part that we will focus on in the upcoming slide. Slick water, which is again like it some sort of a recent activity, is a more tied to the unconventional shale fluid. So it's been developed, I would say, late of 1990, early 2000. That's when the shale start to pick up and increase. And it's mainly for slick water who are looking for a relatively low permeability formation because the leak off will be less. So we're talking about tight gas and shale. That's typically when we are using slick water. If you're still having a high permeability formation, what we call conventional reservoir, in this case, we are still using cross-linked gel. We do not like to use slick water because of the leak off. But if your permeability is small enough to have a very low leak off, in this case, slick water design will be really optimum to be used. And that's why we are using really extensively in shale. So in shale today, everything been done by slick water. There is no much cross-linked gel bumped for shale. You are talking about really high bumping rate. So up to 120 barrel per minute. Usually for conventional frac treatment, we are talking about rate of 35, up to 50, can go 55 as usually the normal upper limit. Let me have it this way. So, but in shale, it's easy to go to 100 barrel, 120 barrel per minute. And the high rate will allow you to have a good carrying also for the proband and place it inside the formation. Volume of the water, we are talking about much higher volume of the water, almost actually more than 500,000 gallon per stage for one frac. Imagine if you have a horizontal well that has 40 to 60 stage, each stage of them using almost 500,000 gallon of water to be able to frac. And again, if you are talking about slick water, it's much simpler and easy to use. And that's one of the key parts why it's working in shale pretty good, because you don't need a lot of additive there. It will be mainly the water part, which is, that's a must you have, fracture reducer, breaker, and whatever additives you need for reservoir. So if you need a scale inhibitor, you add a scale inhibitor. If you need a clay inhibitor, add a clay inhibitor. If you need biocides, add biocides. If you don't need them, you don't use them. So slick water usually a very simpler frac fluid to be used and easier and mixing almost we cannot on the fly. And slick water can be another version of it or another terminology for it called friction reducer. So when, and that's the word of slick is coming from. Something can be bumped really at high rate with a minimum friction reduction. And if you look to the friction reducer, or it's been used in thick water, it is a high molecular weight polyacrylamide, synthetic polymer. So usually in old days, we are using guar, which is around 8 million from molecular weight. Then it came up with the with a friction reducer, a higher molecular weight. We're talking about 12 to 15 molecular weight higher than Gomaa. That is helping significantly. This high molecular weight is helping significantly to reduce the friction pressure. So let me show you on this plot. This is actually a plot. You have here in the y-axis friction pressure in psi per 100 foot. So this value, how much pressure drop you have every 100 foot of pipe. And then you have a pumping rate going from really like 0 up to 100 barrel per minute. And we're talking about a pipe of 4.5-inch tubing. So it's a little bit small size, but it can clearly show you the difference. And we have a 3 type of curves. The first one is just KCl prime, just KCl without any chemical, without anything. Just like if we look to around, I would say like 50 barrel per minute, you are almost 1000 psi for every 100 foot. So to pump through 100 foot, your friction pressure losses will be almost 1000 psi. If you add a little bit of guar, 10 pound, which is not that high molecular weight, still good size polymer, but you can reduce it from 1000 almost to 200 psi per 100 foot, which is pretty good. But if you put the same in a good friction reducer material, which is the red curve, you are talking about 20 psi. So you can see huge benefit of having friction reducer, going from 1000 at 50 barrel per minute up to like 20 or 25 psi per 100 foot. So friction reducer significantly reduce the friction pressure, and reducing the friction pressure, that can open a lot of cases that you can be able to transmit the surface horsepower to downhole with a minimum losses, and can allow us really break a very hard formation without any issue. Because at the end of the day, what you are paid to the surface company is how much horsepower they are using, not how much rate, not how much how can I say it? Not how much it's how much pressure is correlated to the horsepower. So how much pressure that you need at the surface to break down the formation. That's usually the contract point of view. It's not a fixed. It's not a fixed. It's not a fixed number. It's how much horsepower the company need to frac your well. The lower the horsepower is actually the lower money you pay to the surface company to do the job for you. So having the friction reducer, it can easily reduce friction pressure from 70 to 80%. It allows us to increase the velocity during stimulation. So you can start with some sort of a rate, but with time, actually, you can go to a really high rate if it's possible. Usually, we try to reach to the rate as fast as we can. So if you have a lower friction pressure, you can bring your maximum rate as much higher you can. And the rate is really critical for slick water, because right now you are transmitting the proppant not by viscosity, by velocity. So the higher the velocity, the better proppant placement, the better frac you are creating. So simply, if you look to the benefit of slick water or friction reducer, it is giving you a lower hydraulic horsepower at the surface, will give you lower pumping cost, and allow you to pump your frac at a higher rate, which will carry the proppant and place it deeper inside the frac without any issue. And again, reduce how much time it needed. Because if I go to a higher rate, I can pump the job faster. If I pump the job faster, I can pump multiple jobs per day, and that will save the company a lot of money. Any question here? So, okay, how the friction reducer work is pretty simple. So when we are talking about a really high injection rate, you are definitely talking about a turbulent flow. And that's actually having a turbulent flow that's using the friction drop. So you have a lot of vortex in the flow. This vortex consumes more pressure to be able to overcome it and move through the pipes. What's the friction reducer do? the friction reducer is actually long chain polymer having some sort of elastic component in it. Act similarly to the struts in your car, the springs in your car, that when you are moving in a bumpy road, you do not feel it because you have a good spring in your car, good struts in your car. So that's exactly what the polymer do. This polymer, when it dissolves in the water, it actually goes through this turbulence, this vortex, and absorb all the energy that coming from the vortex, allowing it to act as a laminar flow, very pseudo-laminar flow, which will significantly reduce the friction reduction. So that is simply how these polymers is working. So absorbing all this turbulence energy and transfer the fluid to what you can call pseudo laminar flow. So that's why the friction pressure will be significantly lower compared to the flow without the polymers. So, so the friction reducer, how it came from, or the formulation that we are using it, we have a different type of friction reducer or a different forms of friction reducer that can be delivered to the location. The original formulation, which was really most common used up to 2015, I would say, it's called an emulsion product, which is external phase. You have some sort of oil, and you have a droplet of emulsion, like a water droplet inside external phase of oil. You can see the oil. The oil here is the yellow section, and inside it you have a droplet of water. And inside the droplet of water, you will see you're having your threaded chain here is a polymer. That is the most common and the initial way to have this friction reducer. It came as an emulsion product, and that's the way that you are actually manufacturing it. As soon as you creating and the polymerization is happening, you can create this emulsion as a stable product at the beginning. It most common type of polymer is a partially hydrolyzed polyacrylamide with PHPA. And usually this emulsion does not have a lot of polymer from activity point of view. So you are talking about 20, I would say 25 to 35% active polymer in each gallon of emulsion product. So we're talking about 2.5 to 3 pound per pound of polymer in each gallon of the friction reducer, which will be equivalent between 25 to 35%. And again, this is with the initial formulation of that's initial friction reducer was actually coming as the emulsion because that's a way of manufacturing it being created as an emulsion. However, some people further dry it to be able to convert this emulsion to a dry product, which if you have it as a dry product, the activity right now, instead of 20 to 35%, you have almost more than 90% active polymer. So you have a smaller amount, easily to move. From environmental point of view, is much preferred because you don't have any oil or emulsion or surfactant. So it required less volume to move, and definitely from transportation will be much easier to transport. However, dry product will not be can easily handled in the field. We need additional unit. We need to have additional unit called dry add unit, which not a lot of people is good to operate this unit. It needs a good skills, a good field engineer to be able to add this unit, add the polymer to it, avoid all hydration issues that you can have, avoid all fish eyes, and have a good mixing for the dry FR. But if you have a good field engineers, be able to can handle it, that will be a good way and a very easy and cheap way of delivering the friction reducer to the field. I would say in between we can have a slurry part, which is you can get the dry product, some sort of suspended in oil mineral. So in this case, you are trying to get an average between these 2 points. First, when you have a slurry, it's still slurry. You don't need that additives pump to pump it, but you still need a good viscosity pump to be able to pump it. So it will be easier than dry to pump it. And as a slurry will allow us to pump more polymer. So we're talking about right now 4 to 5 pounds per gallon polymer for each 4 to 5 pounds of polymer for each gallon of the friction reducer. So the active component go up to almost 50% right now of polymer inside it. So it's a better way compared to the emulsion. But again, dry will be the best from environmental point of view. Slurry will be the second, and the last one was emulsion. So right now, majority of the work actually between dry and the slurry. And a lot of people right now prefer dry because of the less volume to transport, smaller footprint than the location. However, it needs a good engineer that you train them with time, and you'll be able to do a good job in the field for dry. But that is mainly the three type of how you can deliver the friction reducer. Is it emulsion, is it dry, or as a slurry in the field? So let me skip this one and maybe talk about this test, friction loop. So if you're talking about friction reducer, you need to understand there is a very main test that we need to do. It's called friction loop or friction reduction measurement test. And the whole idea of this test, we try to get some sort of a friction reduction value that will allow us to understand how friction reduction is happening, how much friction reduction I'm using, or the polymer give it to me. So this test can be this is like a systematic of the test how it look like. You start with the reservoir when you have the water at the beginning, and at the bottom of the reservoir tank, you will have there is a suction pipe that will go to some sort of a pump, and the pump will pump it the water at a certain rate, and you'll have a flow meter to measure this rate. And pretty sure during the test, the flow rate is constant. Then it will pass through either coil tube or a straight long pipe, depending on the type of equipment that you are using. Some companies will have it as a coiled, 20, 30, 40 feet. Some company will have it as a long, very long, like 10, 20 feet in the wall, and you can go through it. And at the inlet of this section and the outlet of this section, you will have some sort of a pressure transducer to measure how much pressure is going from point A or the inlet to the exit. And the delta B here will be represent the friction pressure. So what we are doing, we are start injecting first water without any chemicals and getting our zero delta B, how much delta B we have at zero condition, which represent to the water pressure drop. Then as we have stable everything, the flow is stable, the rate is stable, pressure drop is stable, we start at a certain point, usually uh, up to 2 minutes, from 0 to 2 minutes, depend. Sometimes people do it in the first half minute, or some people say, okay, let's wait for 2 minutes and then add it. So it doesn't depend. As long as you have a stable pressure drop, you can start adding your friction reducer. As soon as the friction reducer, what we notice here in this pressure transducer, we see the pressure will going down with time. And that's what we're recording here. As a function of time, you will start with a very stable pressure, like a flat line. And then as you start adding the friction reducer, you will see the pressure is going down. As soon as the pressure is going down, it will start going down until it reaches a point and then become flat again, or increase as a function of time. So we run this test typically between 4 minutes up to 10 minutes, depending on how much time you are pumping inside the field. So how much time the fluid from the surface to the perforation it take. If it take 4 minutes, you are doing it maybe for 5 minutes to some additional time. If it take 6 minutes, 10 minutes, you do it similar to the type that you expected to go through it from the surface to the field with some sort of additional time frame. And then we start calculate something called friction reduction, or FR. That is a formulation that is the pressure drop at time zero before adding the chemicals, which is that's delta B zero, minus the pressure drop at the time whatever we're starting the testing, divided by the pressure drop at time zero, multiplied by 100. And then as a function of time, we are looking to the FR percentage with time. So Let me put it this way. So that is like a typical curve of happening. So initially, that's delta B0. The green line is actually the pressure drop. You can see it is starting like I will say flat line here until the time you will start adding the friction reducer, which is from 0 to T1 is the time that is just water. At T1, you start adding the friction reducer, and as you're adding the friction reducer, the friction pressure will go down until it's a maximum point, which we call it end of T2. That is the time that from this point to end, from T1 to T2, that's we called hydration time, the time that needed to all the polymer get hydrated, get released, and reach to the minimum pressure drop, and then become a flat or depending on the polymer how it behaves. Then actually we usually do not give this green light. What we do, we use this formulation, and that's what we're showing the red curve. That's what we have called the friction reduction percentage, going from 0 to T1, usually 0. Then it go to the maximum value of friction reducer at the minimum pressure, and they stay flat. So that is actually the result that we're sharing. And then we have some sort of like a diagram to tell us what will be the best friction reducer, what will be the bad friction reducer. So I have here several friction reducers, and you can see the red one is the best one. Why is the best one? First, as soon as you add it, you can see the friction reduction go to the maximum in a very small time frame. So this means it hydrate fast. It reached to almost 80%. So the higher friction reduction is the better, is the less pressure that we're having, and the better performing reservoir. So it reaching to the maximum value very soon and stay flat, does not decline. Because what's happening as you are injecting the polymer tend to be uh, decomposed a little bit, broken with the shear. And that will affect the friction reduction with time. So as the time going up, as you are pumping, cycling the polymer over all the time, it start to degrade and they start to having a lower value than the maximum value. So this value, you would like to be the polymer degradation as minimum as possible. So we have it there. We call it like the best one. So if after the end of whatever time that we are selecting, the 4 minute, 10 minute, depending on whatever time we are going through the pipes, if it's between 70 and 80, we call it the best. If it is between 60 to 70%, that is good. Above 50% is still usable in some cases, but less than 50%, that's poor, and definitely less than 40%, that's a bad fluid. We don't like to pump. Usually in current application, we all the time prefer to be in the best region. We like to be prefer above 70%. Even at 60%, we do not want to go there. Even still like maybe acceptable, but in our cases right now, especially if you're having a high stress environment, we like shooting to having the best friction reducer as possible, because it can save a lot of headache in the field from this performance. So let me skip this one. So what's a factor affecting the friction reduction performance? FR efficiency, is this represent how much maximum friction reduction I'm getting? Is I'm getting 80% or I'm getting 60% or I'm getting 40% as a percentage? And the factors that affecting this percentage will be two things. How much polymer content I have, how much polymer I have. If I have a 20% polymer active, that will be lower. But if I have a 50%, that will give a much better amount. So the more polymer I have inside the system, the higher efficiency I'm getting. The second part is the molecular weight. Molecular weight of the polymer is another way to see it as elasticity. The better elastic you have, the good absorbing to the turbulence efficiency as better, and that will improve the friction reduction. So FR efficiency, the maximum value here, to get a better efficiency, either you need to increase your polymer molecular weight, or either you need to increase your amount of polymer that you are pumping inside the system. So a lot of time, the only one that can play with the molecular weight is a chemical company. So as a petroleum engineer working in a surface company or as a production company, you just let these guys know, guys, we need the higher molecular weight polymer to be able to use. But the one that you can be able to change in the field is how much polymer you are using. So if you are seeing the friction reduction at maybe 0.5 GBT is not working good, you start to increasing from 0.5, maybe 0.6, 0.7, up to 1, or maybe higher, depending on how much pressure you have. So it's a knob that you can play with in the field, how much GBT or how much polymer concentration you can have. But if you can in advance work with a chemical company or the surface company to get a higher molecular weight polymer, that will be the best way to go and solve it instead of having to pump more chemical in the field. A second part is the hydration rate, how fast you reach to the maximum uh, uh, friction reduction, which is the time between T1 T2. T2. We need to reach as fast as possible, and that's two parts that you have, and you don't have a control it in the field. These two need to be work with the surface company or the chemical company that you have. The inversion package inside the polymer, so surfactant, if you have an emulsion product, is have some sort of a surfactant package inside it. So the good surfactant will allow to release the polymer much faster and give you the maximum friction reduction as fast as possible. The second one is the polymer chemistry itself. The chemistry of the polymer, you change the ambis, you change the acrylic percentage, the ambis percentage. So play with the chemistry point of view. So in the field, you cannot play with that. If you have a bad hydration, you do the testing, and if you find you have a bad hydration, you just eliminate the product. You don't use it. It is not good for your case. So that's why running a friction loop test before the job is really critical, because you need to be sure you have a good hydration rate in your water that you are applying, because that's really depends on the water that you are using. Pour points, again, something related to the product itself. You need to be sure if you have a slurry or emulsion product, the product can be pumped easily without any issue, especially if you are working in an area like Canada or North America, that the winter time can be really cold and the product will not be able to easy to flow. So in this case, you need to work pretty good on the pour point to be able to pump it in the field without any issue. And again, this is something you need to work with the surface company and the chemical company. Mainly, you need to work in the polymer content and the solvent amount in the product itself. Last thing, salt tolerant. So FR work pretty good if you have fresh water. The 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 less salinity in the water, it is easily make it hydrate and easily make it uh, soluble in the water. The more salt, the more brine that you have. Actually, this brine acts as a compressor to the polymer chain. So if you have a salt water, you need to ask your chemical company to be sure that you have a more acrylic polymer and more ambis in your polymer to be able to be more salt tolerant. So that's actually a shape of the same polymer. If you put it in fresh water, what's happened? There is nothing, there is no calcium, there is no cationic product that can compress this polymer. So as soon as you have it, the polymer chain will be easily expand in the fresh water, giving you the maximum viscosity and the fastest hydration time. However, in salinity water, you are talking about you have a lot of positive calcium, magnesium, ions. That's the two main parameters. Sodium, potassium do the same, but actually calcium, magnesium, and iron is really bad product, really bad mineral that actually compress the polymer and make the chain is the less elastic. And again, if you have a less elastic material, the absorption of this turbulent energy will be less and the friction reduction will be less. So that's why you need to design your polymer to have more amps and that allow to be a little bit hydrated in this salt tolerance part. Yeah, I think we have 2 minutes, but we don't have a lot of still we have. Yeah, let me cover these two pretty quickly. So if you are having a friction reducer, there is a new term called high viscosity FR or high viscosity friction reducer, and that's currently the trend in the unconventional shale, which simply the high viscosity FR is just friction reducer. But either we have a more polymer content or a higher molecular weight. So in high viscosity FR, usually the trend is going from 15 maybe up to 25 million molecular weight, really higher molecular weight to be able to get it. And the whole idea of high viscosity FR will allow us to have a good friction reduction, really good one, like going to up to 80% and stay there all the time, and help us to build the viscosity if we need it. Slick water, if you are talking about slick water, the viscosity of slick water is still like very close to the water viscosity. So we are talking about 1 centipoise. It maybe increase the viscosity of the water a little bit, 1.5, 2 centipoise, but not significantly. The good part about the high viscosity FR, you can actually help to significantly increase the viscosity of the fluid. That will allow a better proppant carrying capacity. So let me show you a quick video. It is a two-slot test, something mimic the frac. You have the injection point from the left side, and you have the exit point at the top point here. And I will have one bumping just represent slick water, friction reducer, and I have one represent the high viscosity FR. And let me see if you can see the difference in the proppant transport between these two. So in slick water, you are carrying by velocity. So as soon as you go inside the frac and the velocity is going down, you can see the proppant actually settled almost immediately. However, in the high viscosity FR, you will see the proppant actually is still being carried, both done at the same rate, and you can see it's moving up. So the fluid is enough viscosity to be able to transport and move the proppant inside the frac and be able to produce it. So you can see the difference. So you have here the dune effect, which is the typical slick water. But here you do not see this building of the dune. Everything being transported, everything being moved. So the idea of high viscosity FR, when we need the viscosity to carry the proppant, we can have it. You can start with a low viscosity, but if you need the viscosity to carry the proppant and the place the gel, you can easily do it in one product. Let me cover one thing here. The additives that you are having to the polymer can significantly affect the viscosity of the friction reducer. So I have here this first, I would say light blue one, which is that's a certain high viscosity of our viscosity as a function of shear rate without any chemicals. So usually you have a good, nice viscosity, but if you add a clay inhibitor, because of the cationic environment of the clay inhibitor, you can see the viscosity going down a little bit significantly. And you can see start the polymer fluctuating. So a lot of additives, especially the clay inhibitor, can significantly affect the fluid viscosity of the high viscosity FR. Adding a surfactant will help. First, eliminate the issue of the polymer fluctuation and slightly putting back the viscosity up of the high viscosity FR. So the main point here, when you are evaluating these chemicals, please do not evaluate it by itself. You need to evaluate the whole package, including your clay inhibitor, including your surfactant, include everything, to be sure you are not missing anything that can negatively affecting your performance. Maybe you can start with a really good product, but you have something in your active chemicals that can significantly negatively affecting the performance of it, make it does not work as supposed to work. And you may have something that can solve it as well. So that's why you need to have the whole package testing. So that's my last slide. So if you have any question, please let me know. So questions came, what techniques are used to measure and optimize the properties of the frac fluid? So depending on which type of frac fluid. If you are talking about slick water, friction reducer will be the friction reduction loop, will be the main test that you like to do it. If you are talking about high viscosity FR, I will do friction loop as well as a viscosity measurement will be the two main part to be able to evaluate the performance of it. If you are talking about cross-linked fluid, it will be viscosity. Viscosity measurement will be the main tool, in addition to the compatibility test that you like to have.
Please, if there is any question, please write it in the Q&A. Dr. Gomaa, it seems like we're done with the questions. Thank you very much for the 2 lectures you gave us for this summer training. Highly appreciated. And please enjoy your rest of the day.
Okay, thanks a lot.
Thank you. Have a wonderful day.
You too.